And dear students, with great pride, the Departments of Physics, Mathematics and Computer Science, Bengaluru North University welcome you all to the one-day National Symposium on Breaking Barriers, Women Leading Innovation in Science and Technology, organized under the aegis of PM Usha scheme. In the landscape of science and technology, women have been powerful contributors. Yet, their journeys often remain unseen or undervalued. The theme, Breaking Barriers, reflects the need to recognize the strength, resilience, and leadership of women who push the boundaries of research, innovation, and scientific inquiry. Today's sessions bring together experts from physics, mathematics, and computer science to share emerging ideas, research trends, and real-world scientific challenges and how women are at the forefront of solving them. To begin this meaningful day on an auspicious note, I now request the students Madhusmita and Anusha from the Departments of Mathematics and Physics to kindly invoke the blessings of the Almighty through a prayer song.
मूषिकवाहन मोदकहस्ता चामरकर्ण विलम्बितसूत्रा वामनरूप महेश्वरपुत्रा विघ्नविनायकपाद नमस्ते 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 नमः शरणु शरणಯ್ಯ ಶರಣು ಬೆನಕ ನೀಡಯ್ಯ ಬಾಳೆಲ್ಲ ಬೆಳಗುವ ಬೆಳಕ ಶರಣು ಶರಣಯ್ಯ ಶರಣು ಬೆನಕ ನೀಡಯ್ಯ ಬಾಳೆಲ್ಲ ಬೆಳಗುವ ಬೆಳಕ ನಿನ್ನ ನಂಬಿದ ಜನಕ್ಕೆ ಹುದಯ್ಯ ಎಲ್ಲ ಸುಖ ತಂದೆ ಕಾಯೋ ನಮ್ಮ ಕರಿಮುಖ ಶರಣು ಶರಣಯ್ಯ ಶರಣು ಬೆನಕ ನೀಡಯ್ಯ ಬಾಳೆಲ್ಲ ಬೆಳಗುವ ಬೆಳಕ ಎಲ್ಲರೂ ಒಂದಾಗಿ ಬನ್ನಿ ನಮಿಸಿ ನಲಿಯೋದು ನೋಡೋದು ಚೆನ್ನ ಎಲ್ಲರೂ ಒಂದಾಗಿ ಬನ್ನಿ ನಮಿಸಿ ನಲಿಯೋದು ನೋಡೋಕೆ ಚೆನ್ನ ಗರಿಕೆ ತಂದರೆ ನೀನು ಗರಿಕೆ ತಂದರೆ ನೀನು ಕೊಡುವೆ ವರವನ್ನು ಗತಿ ನೀನೆ ಗಣಪನೆ ಕೈ ಹಿಡಿಯೋ ಮುನ್ನ ಶರಣು ಶರಣಯ್ಯ ಶರಣು ಬೆನಕ ನೀಡಯ್ಯ ಬಾಳೆಲ್ಲ ಬೆಳಗುವ ಬೆಳಕ. Thank you.
Thank you for the divine invocation. May I request everyone present here to kindly rise for the Nadagite.
जय हे कर्नाटक माते जय सुंदर नदी वनगल नाटे जय देव सऋषिगल दीदी भूरे मकुटल नवमणिये चंदन चंदन ಹೊನ್ನಿನ ಗಣಿಯೇ ರಾಘವ ಮಧುಸೂದನ ರವತರಿಸಿದ ಭಾರತ ಜನನಿಯ ಕಂಜಾತೆ ಜನನಿಯ ಜೋಗುಳ ವೇದನ ಘೋಷ ಜನನಿಗೆ ಜೀವೋ ನಿನ್ನಾದೇಶ ಅಸುರಿಗಳ ಸಾರೆ ನಿನ್ನಯ ಕೊರಗಿನ ಮಾರೆ ಕಪಿಲ ಪತಂಜಲ ಗೌತಮ ಜಿನನುಕ ಭಾರತ ಜನನಿಯ ಕಂಜಾತೆ ಶಂಕರ ರಾಮಾನುಜ ವಿದ್ಯಾರಣ್ಯ ಬಸವೇಶ್ವರ ಮಂತ್ರ ದಿವ್ಯಾರಣ್ಯ ನನ್ನ ಶರಕ್ಷರಿ ಪುಣ್ಯ ಮಂಗಳ ಕುವಿಪತಿ ಕನ್ಯ ಕುಮಾರ ವ್ಯಾಸರ ಮಂಗಳ ನಾಮ ಕವಿ ಕೋಗಿಲೆಗಳ ಪುಣ್ಯಾರಾಮ ನಾನಕ ರಾಮಾನಂದ ಕಬೀರರ ಭಾರತ ಜನನಿಯ ಕಂಜಾತೆ ಕೈರವ ಹೊಯ್ಸಳರಾಡಿದ ನಾಡೆ ನಂಗಳ ಜಗಣರ ನೆಚ್ಚಿನ ವೇಳೆ ಕೃಷ್ಣ ಶರಾವತಿ ತುಂಗಾ ಕಾವೇರಿಯ ವರದಂಗ ಚೈತನ್ಯ ಪರಮಹಂಸ ವಿವೇಕರ ಭಾರತ ಜನನಿಯ ಕಂಜಾತೆ ಸರ್ವಜನಾಂಗದ ಶಾಂತಿಯ ತೋಟ ರಸಿಕರ ಕಂಗಳ ಸೆಳೆಯುವನೋಟ ಹಿಂದೂ ಕ್ರೈಸ್ತ ಮುಸಲ್ಮಾನ ಪಾರಸಿಕ ಜೈನ ಧ್ಯಾನ ಜನಗಳ ಹೋಲುವ ನರಿಗಳ ಧಾಮ ಭಾರತ ವೈದಿಕ ರಾಮ ಕನ್ನಡ ನುಡಿ ಕುಣಿದಾಡುವ ದೇಹ ಕನ್ನಡ ತಾಯಿಯ ಮಕ್ಕಳ ದೇಹ ಭಾರತ ಜನತೆಯ ಪಂಚಾತೆ ಜಯ ಹೇ ಕರ್ನಾಟಕ ಮಾತೆ ಜಯ ಹೇ ಕರ್ನಾಟಕ ಮಾತೆ ಜಯ ಹೇ ಕರ್ನಾಟಕ ಮಾತೆ.
Thank you. Kindly be seated. I now request Mrs. Mubarak Taj, Coordinator of the Department of Physics, BNU, to deliver the welcome address.
Thank you, ma'am. When women break barriers, science break boundaries. Good morning to everyone present here. On behalf of the Department of Physics, Mathematics and Computer Science of Bangalore North University, it is my privilege and honor to warmly welcome you all to this one-day National Symposium on Breaking Barriers, Women Leading Innovation in Science and Technology, organized under the aegis of PM Usha. Though our Honorable Vice Chancellor Niranjana Vanalli sir could not be with us today due to prior commitments, we place on record our deep gratitude for his constant guidance, support and encouragement. We warmly acknowledge his leadership as we begin today's program and we extend our respectful welcome in absentia. With great pride, we welcome Dr. A.R. Usha Devi, Senior Professor, Bangalore University, an eminent scientist, an inspiring mentor, and a guiding force for women in science. We are truly honored to have you with us, ma'am. Welcome you, ma'am. We extend a warm welcome to our chief guest, C.N. Sridhar sir, KS Registrar, Admin Section, as well as N. Lokanath sir, Registrar of Evaluation, and Vasant Kumar BV sir, Finance Officer of Bengaluru North University, in their absentia. We also extend a special welcome to our beloved Director Kumuda Madam, who presides over the session. Welcome you, ma'am. We also extend a special welcome to Ramesh sir, Nodal Officer PM Usha, for his constant guidance and support. Welcome you, sir. Now, we are delighted to welcome our distinguished resource person from the Departments of Physics, Mathematics and Computer Science from various esteemed institutions. Your expertise will undoubtedly enrich today's technical sessions and inspire our participants. We begin by welcoming Sharbari Bhattacharya ma'am, Professor, Department of Physics, Nanabhadhi Campus, Bangalore University. Ma'am, your remarkable contributions to physics education and research make us truly honored to have you with us, ma'am. Thank you, ma'am. We are equally honored to welcome Archana ma'am, Senior Program Manager, Technical, Indian Institute of Science, Bangalore. Ma'am, your rich experience and expertise brings great depth and perspective to this symposium. Welcome you, ma'am. We also warmly welcome Sunil Kumar Hosamani sir, Associate Professor, Department of Mathematics, Rani Chennamma University, Belgavi. Sir, your extensive academic contributions and passion for mathematics greatly enrich our program. Welcome you, sir. We then extend our heartfelt welcome to Chandrasekhar Sir, Associate Professor, PG Department of Computer Science, GFGC KR from Bangalore, in his absentia. We then extend warm welcome to Sugunta Devi Ma'am, Assistant Professor, Department of Mathematics, JB Campus, Bangalore University. Ma'am, your dedication towards mathematics and your commitment to nurturing young learners inspires us all. Welcome you, ma'am. Finally, we extend a heartfelt welcome to Kavita Hanamar Ma'am, Assistant Professor, Department of Physics, National Forensic Science University, Dharwad. Ma'am, your expertise in the interface of physics and forensic science brings a unique dimension to our discussion today. Welcome you, ma'am. So I take this opportunity to thank and welcome Imran Pasha sir, Coordinator PM Usha, as well as organizing secretaries, members of organizing committee whose dedication and teamwork have beautifully shaped this event. Welcome. Finally, a heartfelt welcome to all the teaching and non-teaching faculty members, research scholars, students and participants from various institutions. Your enthusiasm and active participation give true meaning to this symposium. Welcome you all. Let us come together today to learn, to collaborate and celebrate the spirit of innovation. May this day open new paths, spark new ideas and strengthen our collective vision for future where women lead with confidence and creativity in every sphere of science and technology. Thank you.
Thank you, madam, for your warm and gracious welcome. To mark the beginning of today's symposium, we shall have the ceremonial lamp lighting. I humbly request all the dignitaries on the dais to kindly light the lamp.
शुभं कुरुध्वं कल्याणम् आरोग्यं धनसम्पदः शुभं कुरुध्वं कल्याणम् आरोग्यं धनसम्पदः शत्रुबुद्धिविनाशाय दीपज्योतिर्नमोऽस्तु ते दीपज्योतिर्नमोऽस्तु ते दीपज्योतिर्परब्रह्म दीपज्योतिर्जनार्दनः दीपज्योतिर्परब्रह्म दीपज्योतिर्जनार्दनः दीपो हरतु मे पापम् सन्ध्यादीपनमोऽस्तु ते ओ दीपं ब्रह्मरूपस्त्वं ज्योतिषां प्रभुरव्ययः ओ दीपं ब्रह्मरूपस्त्वं ज्योतिषां प्रभुरव्ययः आरोग्यं देहि पुत्रांश्च पतिं स्वच्छामि मे सदा रवेरस्तं समारभ्य यावत् सूर्योदयो भवेत् रवेरस्तं समारभ्य यावत् सूर्योदयो भवेत् यस्य तिष्ठति
something referring to a male. What is the name for a woman fellow? We don't have. Now I can say chairperson, not chairman. But we don't have fellow, a Indian name, but she was a fellow. So let's say that she was a first fellow, and so many others. I can't keep on talking about them. This is first where they went to USA to study Western medicine, and there are people who also went to UK. What is particle physics? We talk about something called as mesons, pion, cosmic ray experiments. There is one Biba Chowdhury who went to UK. She was working on cosmic rays. She found Powell's group. She found pions from their emulsion is what I have read. So these are people who were behind. So we do see their work behind it. So let me go ahead. Some first engineer, microwave engineer, she worked in Indian Institute of Science. So that is long back. So you can see 1922 to 2010 was their period. But that is what I would say. This is just a collage where I want to highlight one more particle physicist, Padma Shri award winner. So this is Rohini Godbole, whom I have seen. I have heard her teaching in a SERC school. What is a research school? After my MSc. So we know how passionate she was. She had come to Bangalore University to give some lectures on Higgs bosons and things like that. The way she talks, you would be mesmerized. That is, her enthusiasm will kind of capture your attention. Then you go back and start studying. What is that? I want to know about it. That kind of a take-home message was given by her. Unfortunately, she is no more. She had done excellent work everywhere she is known. India, not just India, wherever she goes, people know her as Rohini Godbole of particle physics. So I have just kept CERN, that is Particle Physics Center, CERN's women. So Women's Day was celebrated in some point of time. I don't know many people here. So people say how I was got encouraged. It was in one of the schools I saw women teaching, women talking. So that inspired me. I too should move ahead. That is one girl saying there. And this is working for climate justice, that is climate science is very important. So today in this era, we want to preserve our earth for next generation or further. So climate science is being picked up, and there are women who are doing a lot of work on that. And also science writers, many women are doing science writers. I do know a name called Shubhashri Desikan, who was my contemporary. She did her PhD from Institute of Mathematical Science. She writes wonderful science articles. If you get across Shubhashri Desikan's article, so you can see it's very, very physics represented as a science writer. So I call them as women in science. So these are things that is coming here. So I will also say, okay, this is already I have explained. So this is organic chemist, first microwave engineer. So and then Purnima Sinha was one who worked with in Kolkata, first lady to get her doctoral degree from Calcutta University. So long back. So she did a lot of work on X-ray diffraction and things like that. So together these women forged the foundations which today's women in STEM stand for. We are all today, so we are all standing from there. But we have something to fall back and check, and we stand on their shoulders is what I want to say. So, and then there are a lot of initiatives. So the initiative Women in Science from Indian Academy of Sciences, it aims to recognize, document and promote the contributions of women to Indian science. Why we have to do it? Women themselves don't say, okay, put my name into this, etc. They do have to put extra efforts to recognize and really identify what was there, document it, because otherwise it is like the Pennsylvania project where women were, their names were also not known. It had to be dug through. So these people have an initiative in India, Indian Academy of Sciences. So they have they address the challenges related to careers, retention and progression of women in science. That website is what I have written. I will leave this slide You can refer to this and check what is their website, how they go about it. So, and then there is some book called Leelavati's Daughters, which was published in 2008. If you have not heard the name Leelavati, it is in Indian scripts. There was a mathematician called Bhaskaracharya, and he writes mathematics. This is Sanskrit, but he had written mathematics. And mathematics he was referring to, it's a verse form where he refers to some girl, Leelavati. He says, can you solve this? And she solves it, kind of a thing. So nobody knows who is Leelavati. Bhaskaracharya's scripts are there, mathematics. So people refer to the olden day. It is not even kind of, I can't say historically whether she is well known. No, her name is there. So we say this is a hypothetical character. Like mathematicians would know something called as Bourbakis. There is no Bourbaki. It's a community. Several people used to do. Leelavati stands for a woman who had curiosity. She would address a puzzle and solve it and tells Bhaskaracharya. So it is Leelavati's Daughters, which was a book published by Indian Academy of Sciences in 2008. It's only 200 rupees. So BNU library may have it. They can, under this they can read it. It was very inspiring. When I started reading, I couldn't stop it till I finished all the 200 pages or whatever. 100 women were covered under that. So this is something, what I say. Leela means playful. So when we learn, we have to be playful. So Leelavati stands for a woman who takes things seriously, but she has a playful, childlike attitude. So that is what should be with us. So that's what I will say. So I will not skip it. So these are people who talk in Leelavati's Daughters. Many of my friends are there, whom I have met. Their names are there. That is 20th century. 21st century scientists are also there. So this is a kind of what is gender gap in Indian science. Many people have written. This is Prajwal Shastri, who is astrophysics from, that is, she now is associated with RRI, I think. She writes about Leelavati's Daughters. So this is Leelavati's Daughters. They brought in about 100 women scientists of India. So was a heroic effort. Some of these essays were then further copy edited in a volume called A Girl's Guide to a Life in Science, because this keeps going. One has to keep reading this to get inspired. So these are, she writes this, the book broke new ground at multiple levels. Firstly, convincing the Indian Academy of Sciences, which is generally male dominated. So it convinces these as it was a real fate that they could do it. So this stands as a record to pay our respect, due respect to Indian women scientists who worked irrespective of all the barriers. So that is one book which stands here. So another thing that I want to say is there is a gender in physics working group. I had the opportunity to be a member during the period 23-24. Shubhabati Goswami is one whom I had met during my research period in a school. She is a neutrino physicist, but she has deep respect for women to go ahead. So she does many things to balance, gender balance. And we know that in physics, among all other science subjects, percentage of women is very less according to their data. They have a gender sensing also for women in science. So these things they do, and they have a lot of other aspects where they conduct workshops, they invite, that is, women researchers, they have committee meetings, how to improve research students and MSc students, how to help them, and so on. So you can check their website, Gender in Physics Working Group. And I also want to say, that is, this started in 2017. Imagine, it's only 8 years ago. So we wake up at some point, it just pushes us, we have to do something. So that, but still they have achieved a lot of things. So I am giving you their website here, so you can check. So this is one thing. I want to also tell you something that I learned while preparing for this keynote address. You all have heard about STEM. science, technology, engineering, mathematics. But today, one adds a E, A. The A here in STEAM stands for art among STEM. So it's not art of the art variety. It is in science we need it. So they say it brings visibility to interdisciplinary talents which women already contribute. So this is there with them. So I will tell you a little story that is, as a child, I used to listen to some stories told by my grandmother, which I can never forget. So I was when in some of the stories, many stories, women had some talent, but the talent was different from what men have. Men used to go for hunting, they will pay war time, whatever is the thing. But women, there were some 64 vidye is what they used to say, 64. What are they? I don't know. But women used to challenge their prospective brides. There is some swayamvara or some such thing. They will pose a question. Who answers? She will marry them. So, but the kind of questions were very, very interesting. I used to listen to those stories. So, storytelling is one of them, first thing. And also, there are many talents which women possess. Unless we give a chance, it is not explored. So, if you say that, hey, what you are talking is not very, very good, I don't take it, then it's gone. So, it's like a little flower which is very sensitive, we have to nourish it. So that's where people add steam to STEM kind of things, and it brings visibility and it integrates communication, design, storytelling, powerful strengths of many women in STEM. STEM has this, so they have to improve it, is what it says. It encourages human-centered innovation where we have empathy, creativity, and inclusivity. We have to be open to inclusivity. So I would have been happy if there are as many boy students here. So we all have to sit together and be able to discuss. That is the era we look forward. Ecosystem is very important. Let us pave our way to it. So when creativity meets science, more women can step in and lead. So that's what is the idea of STEAM. So then I just want to tell you a few things about my field. So that is where I stand here, maybe 10 minutes. Okay, I will not talk more because I'm a theorist. Theorists will work out equations. So we have mathematical equations connected with physical science. So many students here have learned in their PUC what is classical mechanics. So if I have to tell you how I got interested in science, I didn't even know what is science. I was curious when I was young. I am from a very rural background. I just was reading something you people in this era might not be even know. There was Shivaram Karanta who wrote, so he was a Jnanapita Award Prashasti winner from Karnataka. So he wrote Kannada book called as Vijnana Vismaya. So science. That book was, I got that book and it was extremely, I couldn't keep myself this thing. I didn't know what is Vijnana also, but the kind of things that he explains, it creates curiosity first. And then as I went on, in high school, I was from a Kannada medium school. So we used to be taught theorems. Theorems were called prameya. I think in high school, 8th or 9th, we had 9 prameyas. Each one of that was fond. I was very, very happy with Pythagoras theorems and all that. I read them and I feel it is like, it's mine. So that kind of a feeling. So those things were fine, but still it goes away. After some time, it goes away. So BSc. One more thing is, okay, got good marks. So then I thought, no, I should continue to pursue my science. So when I joined my MSc in Mysore University, some teachers, they revealed how one should go ahead in science. What passion should you have? So I would call my journey as laced with some passion, mainly. So I didn't know anything. If somebody says you have to look for a job, I will say, wait, I finish this and then go. So that was my attitude. So I could manage to be here in front of you. Not that I have done, I don't say, talk about my work, but what interested me. So classical mechanics I teach. Many students here would have learned it in their PUC also. So this is all about what we see, cars, planets, playing, everything I can explain using what Newton tells us. So Newton leads us here, Newton's motion. We are very comfortable with classical physics. So we do, what is that? You have to push if you have to move a heavy particle. But what is the mathematics for it? I know. So I will go ahead. That is very nice to know. We do a lot of analytical thinking and try to understand it, and we are comfortable. But physics doesn't end there. So what we say is there is something that is, these are all classical physics. So gravity and all that. And again, Newton had this. If I have seen a little further, it is by standing on the shoulders of giants. No, men, women, everybody says that. That is humility. But women are more vulnerable to such kind of things, is what I want to highlight. So now, this is what I want to say is quantum mechanics. So if I come to quantum mechanics, many of you who have just got exposed to quantum mechanics will also agree that I don't like it. I don't say that because I breathe. We have to breathe. I have to live on quantum mechanics, and I never felt quantum mechanics was scary when I studied it also, because I had a wonderful teacher. So we see the way enthusiastically someone teaches, we are lucky. So that way. So I am sure that you have teachers, but today what happened is we are open to all media, all that. So we find that more interesting than sit and study. So I will say sit and study. There is a lot of things which opens in quantum mechanics. So I will say it's a very different mathematical tool, and it opens up something which you can never imagine in classical physics. So I don't say what are they. I will only say something like this. Quantum system can be seen. I have created a system that is a particle, let us say. That particle can be, a particle can be what is called as, it has a mass and everything, but it can be a wave also. Wave is like water wave, sound wave. So we used to learn classical physics as water wave, sound wave, wave theory separate, particle theory separate. Newton will talk about particle theory, and in optics we study waves. That there are two different mathematics, branches of mathematics, but quantum mechanics brings them together. That is, it says if you are looking at an electron, it's both a wave as well as a particle. So Feynman would call it a wavicle. One more scary thing. How can I accept it? I don't accept it. If you don't accept the mathematics behind it, you lose. So that's what is the main idea here. So Einstein also said, others said light is a wave. Einstein said light is also a particle. Today we have a quantum light which behaves like both wave as well as a particle. These are something strange. I will only say that Einstein himself did not agree to quantum theory. He posed some questions. He calls quantum mechanics is a black magic calculus. So this is for person of the century, Time magazine, and it is seen everybody like us will read such a magazine. Quantum mechanics is a black magic calculus, is what he had written. So now what I will say is, I had already, important thing is not to stop questioning. That was Einstein's motto. He will keep questioning. And that was the starting point in what I had already showed. And I want to tell you, there is something called as Einstein-Podolsky-Rosen paradox. I'm not going to touch it. I only tell you there is some paradox. It is published in 1935. And as a research student, I happened to read it. Till then, 2 or 3 years, I was doing nuclear physics research, theoretical nuclear physics. So something which Maria Gopert Mayer, who was working. So some calculations on nuclear physics. Once I saw this paper on EPR paradox, I just got converted. I said, no, I have to work on foundations of quantum mechanics. So that was some kind of turning point for me. So then, this is, what is this? I can't explain to you. I will just show you one one or two slides, I want to say EPR paradox was originated in Solvay conference. I'm again showing it. These were conferences where they discussed quantum theory, how to accept it, how to digest it. I have to digest it, otherwise I can't go ahead to work on it. That's what was these things. And then I only want to say there is one component in quantum physics which Einstein's paper brought out. It's called entanglement. We heard the name entanglement by Einstein's paper. What it says is, if you have two particles, I prepare two particles, say for example 2 photons, they are prepared, and I take one photon through a optical fiber somewhere, other one to another lab. And if I do something here, the other particle will change. So that was Einstein's paper had mentioned about such a possibility, and one today lives on this kind of quantum entanglement. People have produced it. Globally one knows what is kind of entangled state and all that. So this is very, very crucial for this thing. Einstein called this, I don't believe, quantum theory allows for if I do something here, that will get disturbed. That is something like ghostly action, black magic calculus. So you have something spooky action at a distance. All that came. Then how do we deal with it? This is 1935. From 1935 to 1960s, people all used to say, what do you say about EPR paradox? They will sit on coffee tables or any other table and sit and talk. Philosophical debates were there, could not be solved. Then I will say there was something which came. This is wave function notation, psi, and this is a war between two theories. Suppose I create a theory which Einstein wanted. Let me repeat. I have Einstein telling me something. I have something else being talked about. Einstein says quantum theory is not good in this sense. I prove it. There is a paradox. And somebody else says, no, quantum theory is correct. Niels Bohr and all his followers. So we have to have a comparison between something that I like. I write a theory and quantum theory is there. Can I compare? This is a war between two theories. Was posed by John Bell and he posed this kind of a question through some inequality. I write a mathematical inequality that should be obeyed by Einstein, what Einstein likes. Quantum theory does not obey it. What will nature say? I live in this nature. I have to do experiment. I can't decide. So such experiments were done, and these experiments were, many experiments were done. I won't tell you. So this is in 2015, many violations of Bell's inequality was seen. What is violation? Violation means quantum theory is correct, good. And the theory which Einstein would have liked, that is, I can see, I can perceive kind of a theory, no, it doesn't work. So I have to take quantum theory. I cannot take it for granted, even though Einstein has said that it's black magic calculus. I can do, because theory experiments proved that this is good. I can't go through details, but it's very interesting if you see these stories. So now I was only wondering about foundations. Einstein's theory, it brought your attention to what is called as an entangled state. What is quantum theory? It is something which is of importance to me. But now we go ahead with what is called as applications. I'm only trying to tell you because this is an era of quantum computing, which is a field that I had chosen. So a few slides to inform you about that. So I will say theorists started thinking about what are the practical aspects of this kind of a theory. So we have, I only say quantum theory had two revolutions. First revolution was when wave or particle kind of a revolution. Now we have, entanglement is known to me now. Can I use it for some purpose? It can be used. So we have entanglement and quantum features. This is second revolution, and it is live now. That is, we are all part of it. So that's what I'm going to say. That is about quantum computers. I will not tell you more. There is something called binary digits. 0, 1. We learn in mathematics, learn binary digits, 0, 1. And write every, say, English sentence or something, put it in binary digits, you will get it. Or any number, write it in binary digits. That was an exercise in, I think, school mathematics. So that is known. But what is quantum? Quantum is something to do with what we say is a superposition. So superposition is a concept which I cannot explain right now. But today when we were traveling, this is again something out of the box kind of a thinking. So we were talking about what is superposition. So we were talking about something past. What do you call past in Indian, this thing? Bhutakal, correct? But Bhuta also means ghost in this thing. They are mixed. You can't make out whether it is a ghost or whether it is a past. So Bhoot is something. So such movies have come where both meanings are there. So quantum mechanics is such a expanded theory where you have superpositions. So if there is a bit in mathematics, 0 or 1 is the value it takes. But a quantum bit, it can be 0 as well as 1 at the same time. So what is the advantage? If you have, let us say, something called as 2-bit system. 2 bits means I can have 0, 0, 0, 1, 1, 0, 1, 1. Everybody knows it. But if I have a qubit state, 2 qubit, I have all at one time, all together. So this is called quantum parallelism, and we do such parallelism. So a qubit, if I have n qubits, let us say 1, 2, 3, 4, 5, 6, n. How many bits that they cover? Bits, number of bits that a n qubit system can cover is 2 to the n. So please listen to me, it's a little calculation. If n is 50, let us say I have 1, 2, 3, 4, 5, 6, 20. 20 qubits can give me 2 to the power of 50, that means 10 to the 15 memory spaces. So that is, even a supercomputer cannot do it. So people have started eyeing towards possibilities using qubits. That's what is the beginning of quantum theory. I am again stopping it. It's made up of, today we have quantum computers, cloud computing facilities. IBM has floated quantum computing apps. Maybe Mubarak madam is teaching you and giving you some projects also. So in this, so these are all well known today. Is there a quantum computer? Yes, it is there. IBM has it, Google has it, Amazon Web Service has it. We do have it, but not on my tabletop. So where are how are they made, etc., can be studied. So I will just say that it is important because if I write an algorithm, puzzle solving, if I have a puzzle solving, classical computer cannot solve something. It's called hard problems, and it takes exponential time, meaning that in real time I cannot solve. Some problems, even life of the universe, age of the universe, if I sit with that algorithm, it won't solve it. So such problems are called hard problems. I don't talk computer science now. So they can be solved if I had a quantum computer, is what is proved. Some people have proved it. So then many things come, and what we say is a quantum computer can do something. If I have some problem, there are n steps there. A classical computer has to do one at a time. But quantum computer can do all at a time. So it will give you optimal results that you want with very quick time. So now a challenge is, can you write an algorithm which a classical computer cannot solve, but a quantum computer can do it faster? That's the era. So this is important even in economics, finance, and drug deliveries. It's a multidisciplinary subject. We need mathematicians, we need physicists, we need statisticians, whatever you call, AI, machine learning, all that is needed in this particular field. So I will just stop it. That's why I told you there are some problems which can be analyzed, and applications are something in biological engineering and cyber security. Nation needs security, so we can use quantum computer. And there is financial services. Instead of my old-fashioned things which are very good, fine, but I can have something out of the box thing which may come from quantum computing. I'm not sure, but that is what people are thinking. Unless you try, you don't know. So people have been trying, and there are some results which are good: big data, data science, and all that. Then one more miraculous thing is what is called as teleportation. Teleportation is something: I stand here, I want to go to university. Can I vanish and go there? If I am a quantum state, I can go. So that is what is shown. I don't tell you details, but quantum teleportation is like your Star Wars movies, Star Trek, where I have trouble here on Earth. I vanish here, go to some other planet, and then come back when Earth is safe. So that kind of a thing was proposed, and it was called teleportation there. But today, what is quantum physics? They name it as teleportation. And as you know, China has already teleported some light or whatever from Earth to a satellite. So India wakes up. All other global people wake up. So it is a global championship that people need. And many are working on what is teleportation. I don't want to say that is this kind of news. You will get it on newspapers also now. So physicists in China break quantum teleportation record. Their record is 870 miles. That is from Earth to a satellite is what they mean. And then there were Canadian research group claims to cross it. People are trying that, and Italy, many places. So we are trying to come there, and I want to say there is quantum internet which is planned. That is, if I have an entangled state between this station, that station, and somewhere else, I can have internet which is quantum. So mobile phones which run on a quantum design and kind of things. I don't know how they work, but that's what is planned. So we need startups, entrepreneurs, and this is another Nobel Prize. First Nobel Prize was given to 3 people in 2022, Alan Aspect and Clausius and Zeilinger. So 3 people. So Zeilinger was the pioneer of teleportation, basically. He was the pioneer. He did in Austria. So these 3 in 2022. So recent 2025 Nobel Prize was given, where one can show that quantum, some circuits, electrical circuits that you have, if you have built it on a quantum computer like setup, some silicon qubits, that some superconducting qubits, they can show effects like tunneling that you have studied. So that is a macroscopic demonstration of electric circuits can also show. I can build a quantum electric circuit. Earlier we used to have transistors, or before that walls. I have worked with walls also. So now today we can have a quantum circuit using this superconducting qubits, and they exhibit quantum behavior. So that is why technology is developing. I want to say it's an exciting time to be a quantum information theory person. I am now curious about experiments. I keep reading what experiments are going on. If I can learn more, that's what I would say. So with this, I will only say that there is a national quantum mission which says for next 8 years, that is 23 to 31, they want to have quantum as a quantum theory, quantum technology to grow. They are funding for startups and students to get fellowships. So many fellowships are being floated. You should be aware about it. And is it possible? So be skilled. If possible, little bit of skills that you develop may help you in various fields. I'm not talking because I work in this field. I am kind of advertising about it. So now this is one thing. Lastly, I want to say what Lokesh, Mubarak all advertised. So I am started my research in 1992 when there was no quantum computing. It was my curiosity which made me take up foundations of quantum theory. So in India, it seems I am the first woman to have worked on this field. And today it has a name. So that era, we didn't have a conference running because it's foundations. Who cares? So today, everybody, day after day, we have one conference on quantum computing, quantum technology. Which to go? I have to choose now. It has become like that. But I should say proudly that I liked it. My passion drove me. So I can't be sure. You have to be skilled. Today, times are difficult. Women still face similar barriers. So one has to cross that, and your curiosity and courage combined, superposed, it should take you ahead in your life. That's all I would say. And thank you. May we continue to ask. Thank you. So I will say, may we continue to ask bold questions and make room for every voice that dares to seek answers. So that's what I want to say and end it here. Thank you very much for your kind attention. I think I have exceeded my time, tunneled through the time. Okay. So thank you very much.
Thank you, ma'am. Watching your smiling face and constant enthusiasm in your voice throughout the session was truly, truly inspiring, ma'am. Your reflections on leadership and role of women in science, especially quantum science and breaking the barriers, truly enriched today's symposium that effectively highlighted the essence of our theme, ma'am. Thank you so much. We are grateful for your time, your expertise, and your valuable presence with us today. Thank you. Now, to formally conclude the inaugural session, we invite Srimati Mamata ma'am for the vote of thanks, after which we will have parallel sessions in different lecture halls, regarding which I'll tell you later. Now, to formally conclude the inaugural session, I invite Srimati Mamata ma'am from the Department of Computer Science to deliver the formal vote of thanks.
Good afternoon to everyone present here. It is my honor to propose the vote of thanks on behalf of the Department of Physics, Mathematics and Computer Science, Bangalore North University, SUVARNA Ganga campus. First and foremost, I extend my heartfelt gratitude to our Honorable Vice Register Admin, Dr. N. Lokanath, Register Evolution, Sri Vasanta Kumar, Finance Officer, the Syndicate and Academic Council members. Although they are not able to join us today, we sincerely acknowledge their support and guidance towards this symposium. I sincerely thank our respected director, Dr. D. Kumuda, for inaugurating this national level symposium and for your inspiring guidance. I special words of thanks to Dr. Ramesh MN, Nodal Officer PM Usha, for his valuable support that made this conference possible under the aegis of PM Usha. My heartfelt appreciation goes to our keynote speaker, Dr. A.R. Usha Devi, for setting a strong academic foundation for the day. I would also like to express our gratitude to all our eminent resource persons from the Department of the Computer Science, Physics and Mathematics who will be leading today's technical sessions. I thank Dr. Sharbari Bhattacharya, Professor, Bangalore University, for accepting our invitation to be a resource person for this symposium. I thank Dr. Archana MS Shri, Senior Program Manager, Technical, IISC, for accepting our invitation to be a resource person for this symposium. I thank Dr. Sunil Kumar M. Osamani, Associate Professor, Rani Chennamma University, for accepting our invitation to be a resource person for this symposium. I thank Dr. Sugunta Devi K, Assistant Professor, Bangalore University, for accepting our invitation to be a resource person for this symposium. I thank Dr. Kavita Hanamar, Assistant Professor, NFSU, Dharwad, for accepting our invitation to be a resource person for this symposium. My heartfelt thanks to the organizing secretaries, faculty members, non-teaching staff, volunteers, technical and media team, and all the students for their dedicated support. I also thank all participants for joining us. Your presence makes this symposium meaningful. Thank you, one and all.
Thank you, ma'am. With this, the inaugural ceremony of the symposium concludes. We now request all the participants and students to kindly proceed for a short tea break arranged outside the seminar hall in the corridor. After the tea break, students are requested to assemble for the parallel sessions as follows. Physics students, please kindly reassemble here in the seminar hall at 12:45 p.m. for the first session. Mathematics students in the mathematics lecture hall and computer science students in the physics lecture hall. Kindly assemble around 12:45 p.m. Kindly follow the direction boards placed outside. Thank you, one and all.
Professor is interested in the effect of various disease conditions and the mechanical properties of the human red blood cells and possible development of new diagnostic techniques based on research. Professor is also in the process of developing a detailed study of magnetophoresis in human blood flow like conditions, keeping in view the possible application of this in targeted drug delivery. To this effect, she is also involved in an effort to synthesize magnetoresponsive biomimetic extracellular vesicles. Additionally, Professor is interested in the development of optical as well as magnetic tweezer-based techniques to elicit information about complex biological systems by exploiting the interaction between micron-sized magnetic beads and magnetic nanoparticles. Further, Professor is also in the process of studying the role of magnetic interactions in self-organization at the macro and micro length scales. Professor has over 40 publications in refereed international and national journals. Three students have already received their PhD degrees under professor guidance, while one more is at the stage of thesis submission. 4 more students are currently pursuing their doctoral degree under professor guidance. Professor has also guided 32 students for their MSc dissertation. Thank you, one and all.
Thank you, Sushma ma'am. Now I request Sharbari Bhattacharya ma'am to take over the session.
Okay. So good afternoon, everybody. Firstly, I would like to thank the organizers for giving me this opportunity. It's a pleasure to be here, to be talking about a bit of my work. I don't think I'm going to go through a lot of detail of that, but mostly on this great occasion when one has decided to talk about the role of women in science. And we had this very inspirational talk today morning by Professor Usha Devi, who's also a great friend of mine. And I was really mesmerized by her talk. It was a wonderful talk. And I really liked the way she kind of went smoothly from physics to mathematics to computer science. I think it requires an extraordinary talent to do that. I was really impressed. Yeah. So just, going to what I have decided to talk about. I'm talking about building a career in soft condensed matter. So of course, I have to explain to you what is this soft condensed matter, right? So that I will do. But what I am basically talking about is a bit of my journey, okay? So in some sense, talking about gender disparities as it exists, and I'll be talking mostly in the Indian context, and how one can go from there to doing something like I have done, that is study red blood cell mechanics, let us say, all right? So you can see a few photographs over here. Some of these people you've already been introduced to. You can recognize Professor Rohini Godbole. Not only was she a fantastic particle physicist, the cause of women in science was very close to her heart, and she really fought. You know, there was this DST Women in Science scholarship which she made available. It was due to her efforts. Okay, and if any woman in science had any trouble, they reached out to ma'am, she would help. And it's a real pity that we lost her, you know. So it just happened this year, right? Last year? 24, yeah. So this is a huge blow actually, but I'm sure there are people amongst you who will take up the cause, okay? The person here, Ashima Chatterjee, I kind of put her especially because she's the first woman to receive a PhD from an Indian university in 1944, before we even got our independence. Like, you know, at that time, women were probably not even allowed to go beyond 10th standard. Okay, so imagine how great that is. Anandibai Joshi, first Indian woman doctor. Unfortunately, right after she qualified, she passed away. But nonetheless, barrier breaking, okay? The lady over there, Tessie Thomas, maybe most of you will recognize her. She's the Missile Woman of India. Massive developments in the DRDO, yeah, Defense Research and Development Organization. And the other lady over there, the lady in blue, Gagandeep Kang. So we all got to know her during the COVID-19, because she is an epidemiologist, a virologist, okay? She studies infectious diseases. So she's now in the Melinda and Bill Gates Foundation, forwarding the cause of studying infectious diseases. Actually, a doctor from CMC Vellore originally. Okay, so now let's just move forward. Let's just start very simply, okay? So what really is science, okay? So let's ask that question. So science is basically an intellectual and practical activity. And what does it involve? You just do a systemic study of the structure and behavior of the physical and natural world around us. You do it through observation and experiment. So in simple words, to put it, science is a systematic approach of trying to understand how the world around us works. Correct? Why does anybody pursue science? First of all, of course, like ma'am mentioned today, curiosity. Okay? You are curious about how this world works. And secondly, there is this incentive that once you know how it works, you can perhaps control it. Correct? You can control it and you can turn things around to your advantage. Think about us. This is not possible in the wild, what we are doing today, right? The only reason it has happened is because we have, in some sense, harnessed how nature works. Correct? So now let's prove, why am I talking about this? Okay, sorry. A breakthrough idea can happen in any mind, right? It doesn't matter our color, our gender, our country, it doesn't matter. A breakthrough idea can come to any prepared mind. So now the point is, if 50% of human beings are not contributing to this, okay? Imagine, all these wonderful things may not happen. Any brilliant idea can revolutionize our world. You know, you could have a green planet. We need one, right? Yes, we could have a cure for cancer. You could have fantastic communications, teleportation maybe, okay? All right, so imagine, all right, so no one in this wonderful process should be forced to be just standing and watching, right? People who want to participate, it doesn't matter where they come from, it doesn't matter their gender, it doesn't matter their color, their height, nothing matters. They should be allowed to participate, correct? Now let's come to some hard facts. Okay, so STEM is a big thing in India. Okay, so I have just quoted some statistics. Okay, in fact, India has the highest number of STEM graduates in the world. So STEM, you already heard, science, technology, engineering, and mathematics, right? No, also I think medicine is also a part of it. Medicine is also a part of it, okay? So now India has the highest number of STEM graduates of the world. And not only that, the number of women in STEM has been steadily growing, okay? Now, so where is the problem? So you can in fact compare the number of female graduates in STEM in India, 42.7%, okay, approaching the 50% mark, mind you, and compare it to US, Australia, and Germany. All right? Sorry, I don't know how I managed to do this. I always do such thing. Yeah. All right. So number of women in STEM in India is really high, and yet here comes the problem. Sorry, what did I do? I have to just slide it, right? All right, only 27% of STEM workers are women. Okay, so 13.5% of researchers in R&D activities in India are women. This is from a Government of India report. So somewhere, women are graduating in STEM, but they are not coming to work in STEM. So we are losing people, right? So basically, this is something which is termed as a leaky pipeline. All right? Lots of women students in STEM, but when it comes to them doing a job in STEM, we lose them. So the question is, why does this happen? So first of all, of course, societal norms, right? Yeah, we are all, whether we like it or not, we are all brainwashed. Yeah, there are certain gender roles which are given, correct? Men do this, women do this. Men, if women want to do this like men, they have to also do what women used to do, correct? Yeah, that doesn't change. So now the thing is that there are family expectations, responsibilities, and why is it a problem only in science? It's actually a general problem. But in science, it's a bigger problem because science doesn't respect this 9 to 5 boundary. If you're a teacher, maybe okay. But if you're a researcher, your research is not going to wait for you, right? Saying, oh, I'll wait till ma'am or sir gets free and then I will do it. Somebody else will go ahead before you, right? So you cannot wait. So thereby, your science starts encroaching, not only it goes beyond 9 to 5, it starts encroaching your holidays, it encroaches your weekends, right? Family time gets shut down. And there are expectations from women, and that is why a lot of women find it impossible to cope with a career in science and managing a family. Yeah, so they drop out. Now, I want you all to look at this riddle, okay? Because a lot of us think that we are actually without prejudice. Look at this riddle. Of course, this is being said in a context, so you will get the answer immediately. It says that a father and a son get into a car crash and are rushed to the hospital. The father dies. The boy is taken to the operating room and the surgeon says, I cannot operate on this boy. He is my son. How is that possible? Now, I think you will somehow iterate onto the answer that the surgeon is the mother, right? But if it has taken effort, believe me, you are brainwashed because you think automatically surgeon, male, right? Yeah. So remember this, out of 40 to 75% people actually cannot solve the riddle. They will think, oh, son, this boy was adopted, or, this is a gay couple. I mean, anything and everything comes into their heads except that this is the mother. All right. And I watched a YouTube video of Indian people being asked this question. Okay, there were about 10 Indians who were asked, only one got it right. Okay, so the prejudice is very strong, and these were all urban, very hip Indians, sitting in big cities who were being asked these questions, right? You'd think they were without prejudice, unfortunately, no. So this is a very deeply ingrained situation, okay? No matter the age, no matter the background. Now, partially, I think women also suffer this from exactly what ma'am told you, lack of role models. Okay, we need to look at women scientists. We need to look at, read about them and somehow adjust our head that a scientist, you can equally think it's a male or a male or a female. Okay, you will not associate immediately a man to be doing a certain job, for instance. So now, of course, there are other reasons. I will not go into too much of detail. But for instance, if there are financial constraints in India, normally the family tends to pitch it behind. If there are two kids, boy and a girl, they will put it behind the boy. Okay, that's normally a tendency. So these kind of issues also happen. Plus, there is lack of mentorship. Okay, networking. Women don't know other women. With all things which need to be changed. And of course, once you enter the workplace, there is a lot of bias, right, against women. Like teaching, I think, is one place where people are happy to take women, but a lot of other jobs, they will say, oh, no, this person going to start a family will take a lot of leave and so on and so forth, and they get into all sorts of, they go onto the back foot. Okay, so motherhood penalty, for instance, is a big thing. And lack of flexibility in timing. So the question is, what can be done? All right. Now, the government has actually put in a whole bunch of initiatives. I've not mentioned the numbers that I really know, but for instance, there is something called Kiran, Wise Kiran. Okay. There is the Curie program. There is the SERP Power program, which are all meant to empower women researchers. There is this one thing I haven't mentioned over here. It's for it's called VOSA. Okay, so that is what Rohini Godbole was also, instrumental in bringing about. It was for women who basically had done a PhD, but then somehow stopped working. It was to bring those people back into the mainstream. Okay, so scholarships for that. Then also, there are other things which need to change. For instance, there is a Maternity Benefit Act. Okay, but if you think about it, let me go back. Yeah. Male employees, okay, don't really get a paternity leave, all right? They get 15 days, but they should be equally responsible in bringing up a child, right? So I think they should be allowed, between the man and the woman, they should be allowed to take equal amount of leave, in my opinion, all right? Because bringing up a child is everybody's job, not just the woman's. Right? And in private sector, there is not even a mandatory maternity leave. This definitely needs to change. Now, in certain universities and research institutes, there's an upper age limit. Now, that's a very unfair thing because by the time a woman has, for instance, done a PhD, wants to go into a job, okay, at a research institute, that will be exactly the time when she's also starting a family. Now, dropping out for a few years is a very normal thing. And then what happens is when they want to come back, they are above that age limit, right? People are willing to relax. Sometimes I was a beneficiary of that, I can tell you that. Yeah, because I was above the age limit of 35. I had to take care of my child. I had dropped out of my job. And if the university had not been considerate, I wouldn't be here talking to you people. Okay? So remember that there are certain things that need to be actually abolished. All right? Now, what can we do as individuals? Now, this is a very important thing. Please, if you are a woman in science, be supportive of other women in science. We need a network. Men already have a network, okay? Yeah? And women need a network. Women need support. Sometimes the family is just not understanding. Reach out your hand. If I'm here today, it's because my friends in the department held out their hands when I needed it. Yeah? So you need to do that for other women, and this has to be without prejudice. It doesn't matter whether you like that woman, you don't like that woman, whether it's your sibling, whether it's your daughter, whether it's your daughter-in-law, please be supportive because women need that support. Okay? Because sometimes things are tough. And as some lady lawyer once said, till every man doesn't go to bed with his last thought being, what should I cook for breakfast tomorrow? What will I pack in my kids' lunchbox? Things are not going to change. Okay? Yeah? So till then, women have to support other women. All right. So now that I've kind of talked about this gender disparity, I will again encourage you. Leelavati's daughters, ma'am has already talked about. She's also talked about the Girl's Guide to a Life in Science. I will recommend these other two books. It's called Lab Hopping, which talks about women in various labs all over India. And I will talk about women in the wild. And that's a wonderful thing about wildlife biologists. You know, women actually going out, pursuing animal, observing animal life in forests. You can imagine how much of prejudice is there against allowing women to do that. That's a wonderful book about these 4, I think, biologists who have been talked about in that particular book. So please read these. If you're looking for role models, some of them will be found here. Right. So now let me just, before I tell you about soft matter, let me just introduce this whole thing of soft matter. Okay. Now, I have given certain examples of soft matter, but I think I will get into it later. Let me just move on further and ask what's matter. All right. So matter, of course, is what we see around us. We are ourselves made out of matter. But normally when you ask a school, any science person, okay, what is matter? I mean, arts people will give you very beautiful but not science answers. But so that's why I'm referring to science people. So they will say, oh yeah, matter, there is a solid phase, there's a liquid phase, and there is a gaseous phase. So right now, let's not talk about the gaseous phase. We are talking about the solid and the liquid phase. And when you think about a solid, you think about a brick like that, right? Yeah. It has mass, it has dimensions. Liquid means something you can pour, correct? Yeah. So like water. So if I want to talk about it scientifically, all right, I will say that the solid shows something called as elasticity. So what do I mean by elasticity? I put a force on it, but it doesn't change its shape, correct? Yeah. So it maintains its shape. So it has an ability to get back. Even if it deforms, it has an ability to get back. And this is what we term under, Hooke's law, right? Yeah. Stress, strain, linear relation, right? So that is what I have shown over there. Liquid, what do you think about on the other hand? You think about it flows. And if something goes inside it, you see some kind of a shear stress. Okay. So there's something called as a viscosity. And this viscosity doesn't depend upon how you're shearing it. Yeah. You apply a force on the liquid, the viscosity doesn't change. So this is what are usually termed as a Hookean solid and a Newtonian liquid. But think about most of the things that we see in our day-to-day life. Are they like this? For instance, in the morning you get up, you're going to brush your teeth. You'll be using toothpaste, correct? Now toothpaste, when it's inside the tube, you open the tube, you hold it upside down, does it pour out? No, it's a solid. Then you squeeze it and it flows out. Then it's a liquid. So what is it? Okay, that's a soft matter, all right? So let's just go over here. So toothpaste, okay? Let's take shaving foam, okay? Yeah, shaving foam, what is it? You can actually make it flow by shearing it. But if you put the foam or press it out, it just stays as it is, right? Maintains its shape. That's the definition of a solid. Then this one, dosa batter. Liquid or solid? Yeah, when you put it on your pan, it distorts a little, but it will stay, right? But when you take that sautu, right? And then you kind of spread it around, it spreads, isn't it? So, most things are neither strictly solid nor are they liquid. They're what we call as viscoelastic. So they have viscous properties as well as elastic properties, and it depends on how much you shear them. Okay, so now the question is, you could have a situation, okay, where the viscosity increases as you shear them more. Think about dosa batter, okay? When you're trying to stir it very hard, it becomes very hard, right? Your hand starts paining. If you do it slowly, you can move it around, right? But if you try to do it fast, it doesn't really thin down. It seems to hurt. Paint, on the other hand, okay, will behave the other way around. Paint, It's very difficult to move the brush initially, but if you keep on shearing it, it thins down. All right. So there are things. So these are materials whose viscosity will actually change it depends upon your shearing rate. Okay, so you can have shear thinning materials, whereas the shear rate increases, the viscosity goes down, like paint. And there could be things where as you shear it, the viscosity goes up. It becomes more and more solid-like. Okay, so that is essentially your dosa batter. All right. So now, the point is that soft materials, no, you can't really, what you have learned in solid state physics, okay, that exact thing will not be extrapolatable to, that's not really a word, you cannot extrapolate it to understanding the behavior of soft materials. All right. And why is that? That is because in the soft material, what happens, your constituent should be, atoms or molecules and the interaction between them. Otherwise, you think that these molecules should get together and you should have long range behavior, right? That's your solid. But what happens in these soft materials is somewhere in between this atom and these long range order, you get some kind of intermediate order. Okay. So for instance, some molecules get together and they form a cluster and they're very happy with that. Then the other molecules get together and they form another cluster. So they form what are called as mesoscopic structures, neither molecule atom nor completely long range. And the behavior of the material is decided as to how this one cluster interacts with another cluster. Problem is those energy scales, right? Everything is a matter of energy. They are comparable to thermal energy scales. That means if you heat a little, cool a little, very weak energies can disturb the interaction between those mesoscopic structures. So which is why soft materials have very diverse and interesting properties, right? So I will move on. So for instance, another second feature of these are, I think I've already explained that they are very, the energy scaling for the interaction between these mesoscopic structures is thermal fluctuation. The third thing is that these tend to assemble, self-assemble. Okay, so if you leave them alone, they will tend to come together and form some kind of an ordered structure. Now, mostly you will feel, how is that possible? We all know that entropy has to increase. So some amount of energy gets consumed, but then it gets into this ordered structure, which, will be kind of if you take the energy phase space, it will be like some kind of local minima it finds, okay? So that is another reason. So for instance, here I have shown pictures of, this is for instance, a lipid molecule. So what's a lipid molecule? It has two hydrophobic tails. Hydrophobic means what? Hates water. And the head is something that loves water. So when you put it into water, what will happen? It will float with the tails up and the head down. Now, if you put a whole bunch of lipid molecules on, let's say, a water surface, they will self-assemble and make a film. Most of our cell membranes are made out of films like that, okay? So this is some kind of self-assembly that they show, which makes their understanding their behavior even more complicated. Now, I'm going to show you this video. This is a very interesting video because when I'm telling you that it behaves in a very strange way, this will explain to you how strange it can be. So now what is happening over here is that people have taken a mixture of corn flour, okay? So 2 parts of corn flour, 1 part water, okay? They mixed it. It's like a very thick, you can call it a liquid. But what you will see over here is that people have put that liquid and they can actually walk on it. So as long as they walk, they cycle, they dance, no problems. The moment they stop, they sink in, okay? So let's see this video. So water and cornstarch is mixed to make this kind of a liquid. It's very thick, as you can see, but it flows. So as long as you're moving, it's fine. So basically a sudden force, it behaves like a solid. And you see this poor guy has sunk in, right? So the rule is don't stop moving. Okay. So I think we will stop this. So I think you get an idea of how amazing the properties can be. So now if I go to biological matter, okay, what makes up? It is basically nothing but a very highly complicated soft matter. Okay, why is it complicated? Because finally, imagine, you consume material from elsewhere, right? Yeah, and it turns into living material inside your body, right? Isn't it? Your cells, your bones, whatever is being repaired is coming from what you are actually consuming from the outside world. So there is a capacity for self-assembly. The maintenance of the self-assembly requires continuous consumption of energy. Okay? Because if we stop, that's why we need to eat food, right? Because just to maintain our system the way it is, you need to keep consuming energy. So it's an out of equilibrium situation. It's not at all an equilibrium situation. So in some sense, understanding the physics of living materials is I wouldn't say ultimate challenge, but it is definitely a very, very it's challenging. Okay, so let's put it that way. So now let's come to some women who work in soft condensed matter in India. I have picked up only 3. Okay, so one of them is Professor Ranjini Bandipadhyay. She's at the Raman Research Institute. You can go and look up her webpage if you're interested in this kind of work. But one of the very interesting things that she actually had done was what I have shown over here. It is a very interesting phenomena called the Brazil nut phenomena. And I think you would have seen this when you have taken a box of mixture, all right? What you want to eat. Shake it. You think that the bigger pieces should go to the bottom. But what happens usually is that they come to the top, right? It's called the Brazil nut phenomena, all right? And she actually studied this, and very interestingly, all the experiments didn't cost much. She used mustard seeds. Okay, so they had, of course, to send it through sieves and get exact sizes of mustard seeds. And she put some big intruders into them, the big thing, and they studied it as a function of disturbance, frequency, and so on and so forth. Some very interesting results came out of this. And the nice thing in soft condensed matter is that you can design very simple, low-cost experiments and work them out. Okay, so she has also very interesting works on clays and granular matter, but nonetheless, this is something of her work which I personally liked a lot. Then this is Prerna Sharma. She's from, okay, very important, I should point out this to you. Have a look here. 28 faculty, 9 women, which means less than 33%. Okay, so I just want you to take a note of that as well. Now let's go to IISc. This is Professor Prerna Sharma. Now Prerna basically, she works on emergent phenomena, basically where, some kind of individual components are there and they get together and you get some kind of a collective behavior. So that is what she's basically interested in. And what she has done over here, so you can see these rod-like objects, right? So these are actually viri, okay, viruses. All right, and they are rod-like viruses, and there is something called as a depletion interaction, because of which they kind of collect together and they end up forming a sheet like this. All right. So now she has an artificial membrane. You really cannot study biological membranes in that kind of detail. So she has created an artificial membrane, and then she puts these kind of beads on it. Okay, and what she finds is that once the bead sits on it, it deforms the surface and it can move in 2 dimensions when it is inside the membrane. But when it goes to the edge, it will only move, it is radially trapped. It doesn't jump off the membrane. It will just stay trapped. So for instance, you can see over here, the bead is moving in 2 dimensions over here, but when it's at the edge, it's actually trapped. Okay, so this is one of her works, which is kind of interesting. The situation I see is not very good. You can see 2 women in a total of 31 faculty. Okay, so pretty pathetic numbers. We need these numbers to be more, we don't want the gender disparity. That should be our final aim. Now, this is Tripta Bhatia. She's from ISER, Mohali. ISER is basically the Indian Institute of Science Education Research. So like, the IITs were meant for engineering. These are meant for the pure sciences. All right. So there are several such institutes. She's in the one in Mohali. And what she does is she's interested in membrane biophysics. So she has done this pretty interesting study. So what you see over here, this is all taken on a phase contrast microscope. So this is a lipid bilayer. I talked about lipids. So this is a lipid bilayer forming a spherical membrane like this, closed, which is called a vesicle. So these are very large microns. You can see them under an ordinary microscope. They're called giant unilamellar vesicles, GUVs. Okay. So what she has done, she has actually kind of changed the glucose concentration inside and outside by putting in some kind of an enzyme. It's called invertase. So then the moment she changes the glucose concentration inside and outside, what she finds is that she can induce curvatures. Okay, see, it's very interesting for us to know how cell division takes place, right? What really makes a cell, bud off another part of it? These are just, these are not really biological, but these are at least things you can study in vitro and get an idea what could be causing these things to happen. So here you can see by changing that, finally she's ended up causing one more bud to just go off. Okay, so this is some kind of work that she does. She also does a lot of other work. I'm just picking up one particular work which I have some familiarity with or I have liked. Now here again you see 4 women in a total of 29 faculty. Okay, so again a very poor number, as you can see. Now, let me come now to finally my work. Now, here I must say that Bangalore University Physics Department is pretty good. Okay, so right now we are 9 faculty, not very high in number, but 4 of us are women. Okay, so at some point we were actually 50-50, so that's pretty nice. But I am hoping that things will get even stronger over the years. So now the question is, when I started studying red blood mechanics, I don't know whether, introductions are given, but normally people don't really register unless there's something remarkable in the introduction of a person. So the thing is that I actually am a solid state physicist, okay? But I was always interested in biophysics, and it took me a little bit of courage. I told you I also had a career break, and it's because people were nice, sympathetic. I had strong women around me who supported me that I could get back into the career. And that is when I took this extra brave step of not continuing with what I had done for my PhD and go into something that I was interested in. And you need to be bold. As a woman, you're already bold. And I think, especially if you're in a career, you're over here in this audience, you're already bold. Do what you want to do. Yeah, do what you want, you really like, because then you will do well, I think. All right. So here, for instance, let's ask the question as to why was I interested in red blood cells? First of all, what are red blood cells, right? So importantly enough, what you have to remember is that in our body, there are about 20 to 30 trillion red blood cells, lot of supply of red blood cells, okay? And, there is, funnily enough, women actually have less number of red blood cells per cubic millimeter than men, okay? It's a funny thing, but it is indeed true. Now, this is a very interesting fact. Approximately, if you take all the cells in your body, 1/4 of them are red blood cells, which is an astonishing fact. So let's just think about what is the shape of the red blood cell. The red blood cell is about, I would say, around 8 micrometers in diameter. Thickness is non-uniform. So it has a thin center and a much thicker rim. So it looks like a filled medu vada, okay? Yeah, so that is the shape of your red blood cell. Now, what does the red blood cell do? Obviously, its job is to carry oxygen. I think I kind of have skipped that, but very key thing in the slide. Its job is to carry oxygen to all parts of our body. Why do we need the oxygen? Basically, it's for the oxidation of certain materials, which will then release energy for us. So without this oxygen supply to each and every part of our body, we will not be human beings. We will not survive, okay? So the point is, the structure is obviously made in such a way that this oxygen supply is done in an optimal way, right? Now, what does this red blood cell have? It has a cell membrane and it has an inside. So this inside is the cytoplasm, okay? And the cytoplasm basically has something called as hemoglobin. What is this hemoglobin? It can basically bind to oxygen. So it binds to oxygen. Then the oxygen gets carried by the red blood cell through a circulatory system. I will come to that. And then finally gets released to the tissues, okay? Now, so that's about the cytoplasm. What about the membrane? So the membrane, okay, interestingly, has, let's forget about everything, just look at this, it has a lipid bilayer. I already talked about lipids. It has a lipid bilayer. Now, of course, lipids there are different kinds of lipids, okay? They're enormous, there's lipid chemistry itself is a branch by itself. So there are enormous number of lipids. So here, it has essentially on the outer monolayer, 2 kinds of lipids. We'll just call them PC and SM. And on the inner monolayer, it has PE, PI, and PS. Okay. Now, this asymmetry is extremely important. Okay. Especially, I think this PS can never come on the outer monolayer. All right. I will just keep an eye on that particular lipid. All right. I will tell you why. Now, supporting this membrane is a structural network of proteins. They form a triangular network like this, and it just supports. Now, of course, as far as our work is concerned, we do not distinguish between any of these parts. We just look at the mechanical properties of the red blood cell. So we treat it as a single unit. Okay. That's heavily phase lagged, no? Yeah, exactly. So now the other thing about the red blood cell, interesting thing which I will tell you, is that it doesn't have a nucleus. All right. Now, if you remember your very key basic biology, you will remember that the nucleus is what basically allows a red blood cell, any cell to divide. Correct? It has the information. And then you can go undergo cell division. But now there's no nucleus, no cell division, correct? Yeah. So red blood cell has a definite birth process and a death process. Okay. So the birth happens actually in our bone marrow. You know the bone. So it's a process called erythropoiesis. Actually, these red blood cells are born with a nucleus, and then the nucleus gets extracted and they get thrown into the bloodstream. Now, let's forget about that. And then let's look at the death process. So what happens in the death process is that this red blood cell is going around in circulation. Finally, it will start exposing some of the inner lipid to the outside. Okay, so for instance, if you remember, there was this PS lipid, right, which was only on the inner layer. It starts getting exposed. Now, when it gets exposed, it's like a chemical flag. All right. So in your liver, there are these things called the macrophages, which just eat them up. All right. So those old cells keep getting taken out and new cells keep getting put in. All right. And then, of course, they don't have also other things like mitochondria. So they cannot really consume the oxygen and the glucose that they are carrying. Okay. They have to produce their energy by glycolysis of glucose and so on and so forth. So let's not worry about that. Now, how does this red blood cell get to various parts of our body? So it does it through the circulatory system. So this is a kind of an idea of the circulatory system that I have given. Here is your heart. Then you have this thick vessel called the aorta, which breaks up into arteries, arterioles, goes into something which we call as a capillary bed, and then again rejoins and goes. So now what you will realize, So what you will realize that in the capillary bed, okay, the channel sizes are the narrowest. Now, if you remember the size of the red blood cell, I told you about 8 micrometers, right? So if the channel sizes are now smaller than that of the red blood cell is going to have to squeeze, deform, and then go through, correct? So now the point is, if something alters its stiffness, okay, makes it more difficult to bend, obviously the entire flow process gets compromised. Okay, so now you may say, when will it ever happen? The problem is there are a lot of common diseases which actually do it. One of the most common things is diabetes. Okay, or what is diabetes mellitus? It actually changes the stiffness of these red blood cells. Another thing is anemia, B12 deficiency. Okay, all of these affect the stiffness of these red blood cells. So how do we actually assess? So that was our interest. Let's find out what is the stiffness of red blood cells. But how do you go about doing it, right? They're so tiny. Normally, if you think about elasticity measurements, you will think about, okay, we stretch it by a certain force and see by how much it deforms, right? But how do you do such a thing to a red blood cell, right? It's a very tiny, 8 micrometer diameter, hardly, 3 micrometer thickness, 1 micrometer thickness in the center. So this is a very, very tiny object. How will you manage it? So the thing is, we use something called as an optical tweezer. And these are some places where we actually flow them through narrow channels. Okay, so these are the two methods which we have used. Now, just to give you a small idea about what are these optical tweezers. So tweezer is something which you use, it's like 2 prongs like that. You use it to hold something, right, and pull out. Yeah? What is it called? Ikula, okay? So, yeah, it's like a bit, like tongs in your kitchen also, right? So those are basically tweezers. Now, what did I say? Optical tweezers, which means that you're trying to hold on to something with light. So I will just try and give you an idea about how this is even possible. How can you hold something with light? All right. So what we normally think about light, we think about things like this, right? we say that, okay, there can be diffraction, there can be refraction, there can be absorption, right? There can be a scattering, there can be elastic, inelastic scattering. So, and then normally we talk in terms of absorption, emission, transmission, and reflection and scattering. And what we forget very often is that light also carries momentum, okay? And the most spectacular example of this is the tail of a comet. So have you heard about these comets? These are these objects which have this wildly, eccentric orbits, okay? So it's elliptical, and the sun is at one of the foci, so it will come in, or sometimes not even a closed orbit. So some comets don't revisit, I think. So when they come in towards the sun, they have this very bright tail, okay, which is always pointing away from the sun. And the reason is that the light from the sun pushes away these particles. So for instance, you can see this is the comet head, and this is the tail of the comet. In fact, you can see a slightly faint thing over here. So apparently the difference between the two is that one is of charged particles and the other is not. Okay, so the ionized particles actually follow a slightly different path, giving a comet two tails. All right, so obviously the light from the sun is pushing it away, so that means there is momentum which is being given to the particles. So basically this is an expression, okay? So momentum, I've written it as Planck's constant divided by the wavelength. Now, if there is a change in the rate of momentum supply, obviously you can put force on a particle, correct? Yeah. So thereby by using light, you can apply force to a particle. So thereby it should be possible for you to hold something. Now the question is, you can ask, why do I want to hold it? So the thing is that when you hold it, you're damn it. Making it not move, keeping it in a certain volume. Okay, it happens to me sometimes. I don't get the word. Yeah. So you're making it stay in a particular volume, and then you have more time to actually examine it. Okay, so the thing is, so there is some interest in trapping a particle. So the question is, can you trap something using light? And this is what this gentleman thought, okay, Arthur Ashkin. And he basically made the first optical tweezer. So his first experiment looked something like this. Okay, so there is light coming, there is a container with some microparticles, and here there is a way in which he can observe it. Now what he found is that all the particles, they got drawn towards the center of this light, this laser beam, and then they moved along the center. Then they came to the other end of this chamber and got stuck. Now, how did he know that it was the light that was holding them there? He just switched off the light, okay, and the particle fell down under gravity. All right, so he knew it was definitely the light which was doing it. So with these imagine that the atom takes in that energy, but the atom is not going to sit with that high energy for very long. It will emit. When it emits, it will emit in some random direction. Okay. So when it emits so now each of this is going to cause a recoil. So when it hits this way, it moves this way. But when it emits, it moves this way. All right. But this emission direction will be random, no? Yeah. But the beam is coming in this direction. So all the time it's getting recoil in this direction. But this other recoil is going to average out. Okay, so there is, in general, a scattering force. So now, what else is there? So let me not get into all of this. There is also something called as a gradient force. Okay, so gradient force has to do with how the dipole moment of the particle will interact with the electric field. All right. And finally, let us say it depends upon the gradient of the intensity. So if you can create a change of intensity over distance, the particle will in general try to go to the place which has the most intense light. Okay. So now, if you think about a laser beam, so if you remember Ashkin's observation, he found that the particles went to the center of the beam, right? So if this is the beam, the particle will go to the center. Question is why? So that is because of the gradient force. Because in general, laser beams have an intensity profile which looks like this. So this is the center of the beam, very intense there, and as you go to the edge, what happens? Intensity reduces. So any particle that is coming in will try to go to the part which is most intense, so it will move to the center of the beam. And once it is at the center of the beam, also more scattering, so it will start moving along the direction of the beam. Okay? So now, if you want to trap, you should do two things. Bring it to the center of the beam, and then create a intensity gradient also along the direction of the beam. Yeah? How do you do that? Use a lens. Correct? Yeah? You know a lens, what will it do? It will concentrate the beam. So you can use a focusing lens, and then you have created a gradient also in the axial direction. So that's precisely what he did. Used a lens and created an optical tweezer. Okay? So now you can use light and you can hold an object. Okay? So now the question is, once you held the object, what do you do with it? You can do several things, okay? First of all, remember, in general, an object, if it is sitting in some liquid, a tiny object, you've all heard of Brownian motion, right? So you know Brownian motion, it will be doing Brownian motion. But now, if you have the object which is sitting inside a trap, and then you are observing it, you may not be able to see the trap, okay? Because maybe you're using infrared light. We are not sensitive to infrared light, right? Our visible range is only VIBGYOR, correct? So if it is infrared, you won't be able to see the trap. But you will be seeing the particle still doing some Brownian motion. But what will happen is that it is a modified Brownian motion. So that extent of the modification will tell you, oh, it's sitting inside a trap. All right? So that is all, that's the kind of stuff you can do. Now, in the case of our red blood cell, what exactly are we doing? This is all, this is all the what I kind of didn't tell you. Finally, Ashkin won the Nobel Prize in 2018 for the optical tweezer. And this is 32 years he set up the original tweezer. Okay? Or he started the first experiment where he just did this single beam tweezer. Now, what I think it tells us is that you really should never give up. He actually started in 1970. And 1986, he had the first tweezer. And then in 2018, the Nobel Prize. Okay? So if you really believe in something, you should just keep working. You should not look for rewards or awards or whatever. It's your passion that should take you forward, right? And I think this man kind of showed that to us. So let me just move on. This is just a citation. All right, so I was just telling you about the modified Brownian motion. So let's move further. Okay, so these are all ways, there's a lot of mathematics. Let's just come to this part, because if we think about our red blood cell, closest approximation to that is a disc, right? It's like a disc like this, isn't it? Now, when I said that, you can hold something in that optical tweezer, I normally was talking about a highly symmetric object like a sphere. So a microsphere, tiny sphere, a cricket ball, very tiny cricket ball you can imagine. That we know how it will get trapped. But now the point is, if I'm going to put a red blood cell, it is more like a disc, right? So what happens to the disc in an optical tweezer is a question we can ask. So what people had done is that they had put wax discs, and this is, what we call as perspex. Okay, PMMA is the word for perspex. It's another kind of acrylic. Maybe you have heard that word. So these are acrylic discs. And what they found is that if this is the beam direction, finally, even if the disc is sitting like this, if the beam is in this direction, the disc actually reorients so that maximum of its volume is in the beam direction. So its maximum volume is seeing a high light intensity. This is, your red blood cell, all right? And when the beam was turned on, you could see this actually reorient and become in this position. So if you look at it, so it doesn't have that position. So this is the final position it will come to. Now, how do I know it has not folded like a chapati, right? Yeah, how do I know it has flipped? Because I'm only seeing from top. I can only see one edge. How do I know it has not folded? So what we did in the lab was that from the side we looked. We put another objectives from the side and you can see a full clear circular cross section. So which means it is actually reorienting. Now the question is, what do you do with this reorientation? Okay, what can you do with this reorientation? So we have taken a video of it, right? So when you look at those videos, you can identify a position where it is flat. You can identify the first time it becomes in this position. And then between the two, okay. So you can identify the positions, the two positions, take the time difference between them and find out the full time it is required to go from this position to this position. So this is something which we call the reorientation time. Now, if I increase the laser power, okay, what will happen is that this process will take smaller and smaller times, okay? So, as I increase the laser power, I expect the reorientation time to keep going smaller and smaller. So this is a theoretical expression of that. Okay, so this is your reorientation time, this is your power, and as the power is increasing, you can see the reorientation time is coming down. This is something that you would expect of a rigid body, and it should go a 1 by power kind of a behavior, okay? Increase power, lesser reorientation time. But now when we actually did the experiment, these are experimental points. You can see them, those black ones. Yeah, we found a problem. If we try to fit such a curve, if we try to fit it for the first 3 points, which is at low power, okay? Oh, it's changed. Thank you. You find that it basically, the curve is the black one. You see? It is not, sorry, I'm bad at this. Maybe I shouldn't touch it. Yeah. So what you will find is that this black curve over here, I shouldn't do this. Yeah, it is not fitting any of the experimental points. You see that, right? Similarly, if I try to only fit the last few points, the last 4 points, that's the red curve. You see that it is not fitting the first few points. So obviously rigid body behavior is not agreeing with this at all. And that's correct, no? Red blood cells are not rigid. Yeah? So what can we do now? What we did was that we said, okay, let us fit it to low power. I think most probably it will behave like a rigid body at the lowest power. It's assumption. And then we will find out how much of excess time it is taking. Rigid body should be black. All the points are above it. So let's find out what is the excess time. Okay. So energy is. So now what we do over here is that we plot that excess energy. Okay, you can see over here. So we are basically the excess energy in the beginning, you know, when it starts parting from it, it'll be very low, it'll go through a maximum, and then finally at high powers, again the thing will start behaving more or less like a rigid body, so it will come back to zero again. But there is a maximum that it has gone through, right? So let's take that maximum and see whether it has some information for us. So what we now find is that anybody who has no medical conditions, okay, this maximum energy lies within a very narrow range. But if they have diabetes, especially if it is without any kind of treatment, then the maximum value becomes something very different, okay, pretty high. So we think that this scales with the stiffness of the red blood cells. So I'm putting it very simply. So we looked at it from people with no medical conditions, We looked at with people who had diabetes but were not under treatment. And the third one, what we did was that we took the red blood cell, changed the environment around it. So what we did was, you know that there are ions, okay, which are always traveling into the red blood cell, going out of the red blood cell. So there is a osmosis kind of a behavior which is happening. Certain water is going in, water is going out, and some way it is being maintained so that the shape stays the same. But now, suppose I take some little bit of acid and put it outside. What have I done? I have completely changed the pH. If you remember your chemistry, okay? I've changed. We now have a factor which is scaling with the stiffness of the red blood cell. Now what this experiment shows is that, you know, if you take it to a person, okay, somebody who they will say, oh, you got this person with diabetes. How did you know that when this person did not have diabetes, that their red blood cell membrane stiffness was not high already? How do you know that the red blood cell membrane stiffness increased because of diabetes? It's a fair question, right? Because I did not know that person when they didn't have diabetes. I didn't measure it then. I'm only measuring now when the person already has diabetes. So how can I prove such things, right? So what we decided was that let's try to do this experiment with altered stiffness. Okay, I know I'm changing the stiffness, and then see whether my optical tweezer result is the same. So this was an artificial way of changing the stiffness. There's something which we call as bovine serum albumin, BSA. Different concentrations have been used. Same experiment has been done, and the stiffness has been altered. So now we can see from a diabetic person, we got something around this area. So this is being covered. We also know less stiffness is there, normal is there. Now what we did was that we said, okay, let us do with these red blood cells what will happen to them in blood flow. So in blood flow, what do we know? They get taken to capillaries, right? So we said, let us take them through flows. Okay? How much time do I have? No, how much more time? Just tell me. 20 minutes are there? Really? Okay. I thought I've been talking for a long time. Okay. So fine. I mean, don't worry. I'll try and keep it light. So this is the flow experiment that I was talking about. Okay. So in the flow experiment, what is happening is that, okay, you want to flow red blood cells, you need narrow channels. What kind of narrow channels? What we find in our capillaries, right? Now capillaries, I should go to 5 micrometer, 8 micrometer, 10 micrometer. Where will I get such channels? That's the question, okay? So one is, of course, you can have microfluidics experiments which can actually make this for you. But, you know, at that point of time in the university, we didn't have much money. So we thought we should try some other clever techniques. So this filter paper you see over here, it's something called as a cyclopore filter paper. 10 minutes, okay. So cyclopore filter paper. So in this cyclopore filter paper, what happens is that it's actually a material, and then you send an ion track through it, okay. You send fast moving ions through it. And when the ion passes through that filter paper, it moves first of all very straight, and it does some damage to the membrane, okay, in the track that it is going. Then what you do is that you apply some chemical, and the chemical etches out. Etches out means it removes the material where the ions have already passed. All right. So what is the end result? You get this beautiful circular single diameter. It's not like it's going bigger or going smaller. You get this beautiful straight circular cross section channels. Okay, so we managed to get 2 of them. They are very expensive. So we managed to get one 5 micrometer, one 8 micrometer. Now think about it. 5 micrometer is smaller than RBC size. So when the RBC wants to go through it, it has to deform. And the other one, 8 micrometer, is the exact same size. No deformation required. So this was very good for us. Okay. So what we did now, so that's our syringe pump, okay? And this is the setup, very simple setup. And all samples were given by volunteers, which was mostly me and my student, okay? Right. So now what is happening over here? So what is being changed in the x-axis is the BSA concentration. So in your own minds, change it to RBC stiffness, okay? And on the y-axis is the number of red blood cells going through per minute. So it's a flow rate, number flow rate. Okay. Now what you can find in the 5 micrometer, what is happening, that is, okay, so let's look at the 8 micrometer first. As the stiffness is increasing, the number that is flowing per minute is actually going up. So that means somehow if the red blood cell is more stiff, it moves faster. Okay? Yeah? Whereas now when it in the 5 micrometer, it cannot move without deforming, right? But now when it has to deform, what is happening over there? As the stiffness is increasing in this one, you can see that the number keeps going down, right? So, yeah, so this is, we kind of tried to figure out the stiffness. So we said the time, there are 2 times we can think about. One is basically the time of passage through that circular channel. And in the case of the 5 micrometer, that passage time is there, but there is also now a deformation time. So more time is being taken. So now with a lot of analysis, we managed to get that deformation time. Okay, so we had to do some kind of theoretical modeling and stuff like that for the red blood cell. So this is all the calculation. I'm not going to get into any details of them. So we got the deformation time. This is how we imagine the red blood cell is deforming. Okay, and now what you can see is we extracted something which is called as a bending modulus. Okay, so which is from the energy of deformation, from the time of deformation, we got the energy which is required to do the deforming, assuming that that energy is coming because of the blood flow. See, once the red blood cell has deformed, it is sitting blocking the pore, right? Meantime, blood is continuously flowing. So that blood flow will push it through. So that energy we calculated. And from those two, we managed to get something called as the bending modulus. Like you have Young's modulus, bulk modulus, and so on. We got a bending modulus. And what you can see is that as the stiffness, BSA concentration goes up, the bending modulus is also going up. Now, what we did was, we compared this with our delta E values. Optical tweezer, right? We had that excess energy value. So for that and this bending modulus, we did a comparison. And you can see it's a beautiful linear fit. Okay? So this was our work. But of course, blood flow is not through nice, neat channels, right? In our system, what is it like? It's like a bunch of capillaries. So it looks more like this. So this is something which is a cellulose acetate filter paper, all right? And they come with some kind of a particle retention size. So which means that if the something is going through, say a particle size or retention size of 1 micrometer, it means that as something is passing through, in the thickness of that filter paper, definitely it will encounter a pore which is 1 micrometer. That means anything which is larger than 1 micrometer cannot pass through. Okay, so that is what it means. So now you're not dealing with a uniform pore size, you're dealing with a whole number, different pore sizes, correct? With a certain probability distribution. So what we kind of have done, we have done the experiments here, but they are fairly inconclusive, and we are not able to take this further till we get a pore size distribution from some other experiment. So we tried, so there are methods called as mercury intrusion porosimeter, but very difficult, and it's very, difficult to get people to do this experiment for us because mercury costs a lot and it's also very dangerous and people are scared to do it, okay? So that's not a method. So recently we have tried to do scanning electron microscope images and try to get a pore size distribution. But here I want you to note something interesting. At high pore sizes, okay, you can see again, stiffer it is, more numbers are going up, okay? Here data is not very great, but at low pore retention sizes, you can see as stiffness increases, it goes down. But here and here, something very strange is happening. It seems to be that optimum stiffness sends maximum blood flow. But till we get a pore size distribution, we will not be able to understand this any better. Okay, and this is probably what is happening inside our body. Okay, not the other one. That's a very, an extreme case. So these are some other measurements. I will not talk about it because I haven't given you the details. So what I would like to give some acknowledgements over here. So the first set of people are basically former and current members of the Tweezer lab. The lab was built by Professor Sharath Ananthamurthy, currently Vice Chancellor of Kuvempu University. And these are a whole bunch of students who have worked on this. Sahana S is currently the student who's working still on red blood cells. She's doing her PhD right now. And what I have talked about, most of the work is based on what Rekha has done. Okay, she's currently an assistant professor in PES University, and also with able support from Praveen and Shruti. Okay, Chetna also did some red blood cell work, but she did it with AFM. So I have not really talked about her work at all. And the others are all members of the, I think Rekha's name has appeared twice. Anyway, it's her work, so more credit to her. All right, and of course I have to thank all these funding missions, the DST Nano Mission, PERS, UGC CPEPA, UGC NET for giving scholarship to some of my students. Rekha was benefited by that. And of course, the Bangalore University Internal Research Fund. So with that, I think I will stop and say, Oh, Chetna was on the VOSA, but I haven't really talked about Chetna's work. That's the reason, yeah. But I should have mentioned it, yeah. That would have been quite apt. No, it would have been apt, I think, yeah. So thank you very much for your attention. And if there are any questions, any queries, any discussions that you want to have, I'll be very happy to answer. Yeah, thank you.
Any question? Okay. So I guess there are no questions from student side. I think biology closed. No, they were curiously sitting and listening to you, ma'am. Thank you so much for your wonderful talk, ma'am. From MSc days, I was curious to listen to your research work, ma'am, but I didn't get the chance. So today I sat and I listened to you very much. So it was very wonderful, ma'am. Thank you so much. So now we will have a lunch break time. After that, the session, afternoon session, Kavita ma'am, Hanama, she will continue. So it's a break for lunch. Ma'am, before that, can we have a group photo because with our students, it's a request.